They're hard. There's guidelines, but no one way right answer. I hope you all worked through at least some of these, hopefully all of these programmed exercises. Covering them up, watching how they did it. I know I had a couple questions. People were like, how come this didn't reset here? And like, there was a few key words, like in this one, what does it mean to be exactly 2 zeros? Does that mean 2 or more? No, that means exactly 2. So this wording, all these wordings are very important to understand what it is that the behavior that we want. And trust me that their answers are correct for this. Okay. There's nothing wrong with the first 3. And in here, we looked at these. We did, I think, problem 14.4 rather, completely in class. 14.8 I kind of hinted at and showed a starting point for it. And this one I want to just do, well, did anybody, any questions on this one, 14.13? Did you get it if you tried it? Didn't try it? Yes.
Do you want us to make the state graph, the state table, both?
Yeah, good question. A lot of these, sometimes they ask for the state graph, sometimes they ask for the table, and sometimes they ask for both. Or, in one case, I think they ask for or. It's kind of weird. Here's my opinion and what I want. The state graph always comes first. Okay, do the state graph. If they ask for a state table, then you have to, in addition to that, guess, then give me the table as well. There's maybe one exception to that one, and it actually might be, well, it's the former one. This one does get pretty nasty. I will say this, on 14.8 it does ask for a table. And, okay, we have 11 states. How many arcs exit every state when we have 2 inputs? 4. How many arcs in this state graph?
44.
44 arcs. It's kind of a nasty one, you know, but that also means it's like 44 with 4 rows if you do a tall, skinny table. That one, the table is probably easy enough. By the way, that one answer is in the back of the book. So, just let you know. Let me just speak quickly to this problem. Last night, or the morning section, I did it completely, and I don't have time to. Somebody read this for us. David, would you read this for us? Just read part A for me.
A Mealy sequential circuit has one input X and one output Z. Z can be 1 when the 4th, 8th, 12th, etc. inputs are present, and Z1 equals, and Z equals 1 if and only if the most recent input combined with the preceding 3 inputs was not a valid BCD encoding for a decimal digit. Otherwise, Z equals 0. Assume BCD digits are received most significant bit first. Derive the state table.
Okay. Again, I like to pick problems that have some semblance of practicality. And this one is kind of neat. So this one, they're going to be feeding us a serial stream of data that are 4-bit blocks. They're 4-bit chunks representing a BCD digit, hopefully. Okay? So, let's do the input-output. Make sure we understand the problem. Say I pick this number right here. Now, it is important which way do they come in, the MSB first or LSB first? What did it say? Most significant bit first, right? So the first one, and this is what we say is the first, right? Second, third, this would be the 4th here. So this is actually the MSB, right? And then it would go down here to the LSB. It would be the 4th one. So looking at that, what number is that? That's the number 5. Is that a valid BCD digit? Yes. Does everybody remember? The valid BCD digits are 0 through 9. A through F would be invalid. Okay? That's the deal. So we're trying to check for these. Is it invalid or not? So in this case, I want you to see this, that these first 3 are mandatory zeros. That's what it says. Otherwise, it equals 0. So on the first 3 clocks, the first 3 inputs, this thing is 0. But on the 4th, it could be a 0 or it could be a 1. It will be 1 if the BCD digit is invalid. That's the statement of the problem. Okay, so we're going to say, so in this case, was it valid or invalid? It was valid. It was okay. It was a BCD digit, so we're not going to flag this as bad. In essence, this is just kind of checking everything should be good. Occasionally, if we get a bad one, it's going to raise its hand and say, whoa, that last one was something's wrong with it. It wasn't a good BCD digit. Okay. Now, there's something else that happens in these machines, and we're going to see another one, and I'm going to do it more thoroughly for you, is that after the 4th bit, I'm going to kind of just draw a line here. I'm going to label it reset. And where's this coming from? Right here. Z can be 1 when on the 4th, 8th, 12th, etc. inputs are present. Okay? Because we're getting them in 4-bit chunks. That's what a BCD digit is 4 bits. So our machine has to self-reset. You know how like one of the previous ones we did where we're filling our little peep things? We said an external thing would reset us. This one we have to internally reset. We've got to do that. Okay. All right, let's try another one. Just to see if we got this. Oops, sorry. What if I got the next 4 digits were 1100? What would happen? What should be the first output here? 0. Guaranteed, 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 right? These first 3 are all guaranteed zeros. But how about that 4th bit? What's it going to be? It's going to be 1. Because 12, right, C here in hex is too big. That's not a valid BCD digit, and we're going to indicate it right there. Okay? So that would be on the 4th. Here was the 8th. I could pick maybe this one. What if we got 1001? Again, these first 3 have to be zeros, right? Maybe I could just do that in all cases. Those guys have to be zeros. But on the last bit here, what do we think? 0. It's okay, right? That's a 9. That's not invalid. So we're going to go ahead and say 0, and we would expect another reset to occur, a self-reset. All right. Now, a couple hints that I'll give you. I'm not going to do this problem for you, but I'll give you a couple more hints. What do the states need to keep track of here? And let me kind of do it this way. All right, we only get to see 1 bit at a time, right? So it comes like this. What are we thinking at this moment? It's BCD right now. It's valid. Right now, we know that this one's valid, right? Because the biggest it could possibly be is 7, right? The other 3 ones, so it's either 7 or less, isn't it? And so you said it would be valid. We know, right? How about if we got to this one right here, the second set? Do we know for sure? We don't really know yet because that's actually the same as this one, isn't it? So what would that state be?
Go to the next, test the next.
It may or may not be valid, right? So this is what we have to remember. So if I were to tell you and how to name these states, we have to know if it's valid, invalid, or I'm not sure yet. Yet to be determined, may be valid. Okay? We can maybe call this maybe if you want. What else do the states have to keep track of? Okay, you're onto the right thing, Christopher. He said reset, but how do we know when to reset? On the 4th one. So what do we have to keep track of? Yeah, which bit we're on, right? We have to keep track of which bit we're on. So the other thing that we're keeping track of is which bit. So let me at least get you started on this. What kind of machine is part A? See, it's mealy, right? Okay, so we're going to make our key. We say S of N, X all over Z. prefer, we always start here with S0, the reset state. Now I'm going to give this a little bit better name. I made a big deal kind of last time. I'll make a bigger deal hopefully now. If you name your states well, you probably understand the machine and know what to do with it. And you probably get it right. So what I really want to do is name the states according to these two things. So what would state 0? What bit am I on? Well, I'm really on the first bit, which is the MSB. That's the bit I'm going to process coming out of state 0. Correct? The MSB bit. I'll call it the first bit or MSB. Now, what is it in terms of this? Is it valid? Invalid? It's a total maybe, right? I have no idea yet in this state. Nothing's happened yet. So it's just maybe as far as the valid goes. I have no idea. All right, let's take off from here. If I get a 0,
Valid.
Josh says valid, right? We're going to go to a valid state. So this is going to be S1. It's going to be valid for sure, kind of exclamation point. We're done. We know anything beyond this, anything coming out of this is going to head on to a valid state. And it's which bit now? It would be second bit valid. That would be its name. What should we output here? 0. It's a mandatory 0 for the first 3, isn't it? Remember these outputs here? They're all zeros. Only on the last one are we going to get anywhere. What if I get a 1?
Don't care.
I don't care?
I can go to the next stage. Is it?
Do you mean out of S0 or out of S1?
Sorry. Out of S0. If I come out of the S0 with a 1, I'm going to output a 0, right? I output zeros on all of them on the first 3. Can I go to this state? No. I need a new state. It's going to be S2. What's its name going to be? In terms of valid, which one is it? Is it valid, invalid, or maybe?
Maybe.
It's a maybe state again, right? What we do know at this point is the leading one's a 1, so if it ends up that or that, it's okay. But anything else is going to be too big and will be invalid, right? So we're going to write maybe and second bit. All right. So from here, you'll have some more states. I'm not going to show them to you. But I just want to say, I'm not going to label these for you. Here was 1, here was 2, here was 3. What happens on the 4th one?
Back to reset.
Yes, these guys must go back here no matter what. If these guys are coming down here, and there may be some different states here, I'm not saying, but this one down here, where does it have to go? Back to reset, okay? So that's the basic structure of this one. And you're going to have to kind of fight out the mid-zone here, but it just label them accordingly, right? And only these arcs could possibly have 1s on them as far as the output. In fact, if we're on the valid side, they're not going to be. But on the invalid side over here, there will be a potential for an output of 1. Okay? All right, I think you guys can handle that one. Especially, I'm going to show you one that's kind of similar to this that we'll work through. So what I want to do with the remainder of our time is I'm just going to help you give some hints, and we'll actually work through, hopefully, several of these problems almost to completion. But 1426 and 1430, I don't think these are going to be too hard. These are really sequence detectors, pattern detectors. This one's looking for 0, 1, 1, and every time we get it, the output changes. It like flips over. Now we output all 1s until we get a 0, 1, 1 again. As soon as we see a 0, 1, 1, then we flip back to outputting 0. And then we're still looking for 0, 1, 1. And once we see a 0, 1, 1, then we flip. See that? So it's kind of a pattern detector. Instead of going back to the beginning, we go to another one. This is a Moore machine, so it's kind of like having 2 pattern detectors back to back. One that's outputting 0s, one that's outputting 1s. You'll get that. Here's one where we're looking for the sequence 0, 1, 1 or 0, 1, 1, 1. Now, Z1 to if Z1 becomes 1, which is detecting this, if we get another one, Z2 will become 1, okay, on the next clock cycle. So we either get 0, 1, 1 or 0, 1, 1, 1. But after that, we're kind of stuck until we get a 0 again to start over the sequence. So I don't think you'll have too much time with a hard time with that. I would encourage you, actually, if I jump all the way back here for a second, those problems, those two problems really, both of them, if there's only one or two sequences that lead to a non-zero output, a good way to start would be to construct a partial state graph for those sequences. So you could do that just super fast, right? What am I looking for? A 0, followed by a 1, followed by a 1. Right? That's what I'm looking like. And then you can go and fill in the rest. And that'll be a good start for you. So, but I really want to keep moving because you'll be happy if I do this one. And I'll try to work through 1437. I've been known to give a problem like 1437 or 1438 on my next test. So I'll just say, pay attention. Don't always, but probably, I don't know, more than 50% of the time I give a problem like this on the test. Because it's really easy for me to change it. And instead of adding 2, I could add 5, or add 6, or 2, or 7, or something else. So anyway, Daniel, would you read 1437 for us?
A sequential circuit has an input X and two outputs S and V. X represents a 4-bit binary number N, which is input least significant bit first. S represents a 4-bit binary number equal to N plus 2, which is output least significant bit first. At the first time the fourth input occurs, V equals 1, if N plus 2 is too large to be represented by 4 bits, otherwise V equals 0. The circuit always represents or resets after the fourth bit of X is received. Find a Mealy state graph and a table for the circuit.
All right. Again, this is a conceivably useful machine. In fact, this got left up here from my 830 section. Ever seen this equation before? Yeah, right? So if you think about doing math, and we do a lot of linear kind of math problems, what is this piece right here? That's adding a constant, isn't it? It's just adding a constant. That's what this circuit is going to do sequentially. It's going to add a constant value to an incoming bit stream. Okay, so there's going to be 4-bit numbers here. Now, they're saying that this is the number 14. Does that bother anybody? Doesn't that look like 7 to you? Oh, but how do these come in? Least significant bit first. So they're kind of backwards for us. So if you flip that around, that is the number 14, isn't it? Okay, and it's very important that they gave it to us least significant bit first. Now the problem we just did, they gave it most significant bit first, and that was handy for doing the BCD checker. In fact, it worked out really nicely for doing it that way. But if they gave it to us MSB first on this problem, it'd be horrendously difficult to do. You'd almost have to store all the bits, add the number, then get the result, and then reverse it to send them back out. So, trust me, this is a very good idea that they gave it to us least significant bit first, because how does a math problem work? This is really what we're doing. We're adding a constant. And we're going to make a state machine do this for us. So the real problem here, actually, red's probably not this. The real problem is we have significant bits of X. We're going to be adding this. We're going to be adding the number to the number. I don't know what it is. It's going to be the 4-bit number. In fact, our state machine is going to be able to add 2 to all possibilities 0 through 15. But we're not going to solve it like that. We're going to solve it 1 bit at a time. So let's make sure we get this first. And let me do this problem. Actually, yeah, I should probably do one that's not symmetric, just so that you can see it. Let me do this. Well, that's the one we already did. Sorry. Let me do this one. Sorry. And I washed the eraser, and now it's wet. It's not working on the board. Oh, okay. Let's try over here. 1, 1, here we go. 1, 1, 1, 0. What number would this be?
7.
That's the number 7, right? Okay, so 7 plus 2 should be 9. All right, so what we're going to do is we're going to get a 1 here. What should we output? We should output a 1, and notice there would be no carry, correct? We wouldn't carry the next column. So what we do is we put a sum of 1 out. Great. Now on the V bit, sorry, let's just do it. The first 3 V bits, I can tell you what they are. They're guaranteed to be 0, just like the BCD checker was. It's only useful on the 4th number, the 4th bit. And, that's what its purpose is. What the overflow bit is here, by the way, does anybody know why we use V for overflow? O is the bane of DLD. We will never use the letter O for anything in here. It looks like a 0. So we'll never do that. And so we pick the second letter, which is V. And we use the letter V for overflow. Which confuse the daylights out of people. We have the letter O, which looks identical to the number 0. So anyway, that was just for free. All right, so here we go. What if the next bit comes in as a 1? Right, that would be, so we got the first bit, now we're processing the second bit. What should we output down here? We should output a 0, but there's going to be a carry now, right? Our machine's going to have to keep track of that. So we're going to output a 0 here, and we would have a carry active. We get another 1, this one right here. What's 1 plus 0? That's 2, right? So we're going to output another 0. Have this carry. Now the last bit's coming in as a 0 in our example, right? What should we output? A 1. Is there an overflow or a carry out? It's a 0. So now notice we output that 1, and this one has an option, right? That bit position right there may or may not be 0. But that's the only V bit that could be non-0. Right? Hey, did it work? Is 7 plus 2 9? Notice we wrote it out here. We got at least significant bit first. So you have to kind of do the reverse, but 9 is symmetric, which is kind of nice, although it might confuse you. Okay. What happens if we get a number that's too big? Then, in essence, this V bit, now bear with me, we have to reverse it. If you just put that bit right here, it'll be the right answer. Correct? What is 14 plus 2? 16. So this really just carries the 16's place, which could happen, right? If I have a number 15 and I add a couple to it, that'll be 17. And so that's V's job. It's really to hold that extra bit position for us and to indicate that it was too big. But if we could just slide that in there, we'd actually have the right answer. So we kind of have to have an extra bit to do that. All right. What do we need to keep track of in this machine? Well, what happens after the 4th one here?
Reset.
Yeah, there's a reset here. All right. Do we have to keep track of which bit we're on? Yes. Okay. So let me do that. That'd be right here. So, which bit? Let me give you a hint. If you have a machine that has to keep track of which bit they're on, you will never hover. Does that make sense? If I have a state and it goes back to itself, how many times have I traversed that path? I have no idea. It could be one time, it could be a million times, right? That I did that. So We can't, if you have a machine that keeps track of which bit, don't you ever hover. That will be a mistake. Because in essence, there's kind of two things. If you have to keep track of which bit, you're really counting. It's like a counter. We've made those already. But we're not just counting, we're also doing something else here. We're adding. So what will the states have to remember? Not only which bit, but any ideas what the other thing is you have to keep track of? Good. Who said that? All right. Good job. So, is there a carry or not? That's the other thing. Carry or no carry. And it's like bowling. It's like to bowl, right? If you get a spare or a strike, can you add up your score right now? No. You have to wait until you throw the next ball or the next two balls, right? So it's kind of the same thing, that the state is going to keep track of that carry, and that output will come out eventually. But we have to differentiate. Is there carry? Is there no carry? All right, so this machine, what kind are we supposed to build? Mealy or more? It does say somewhere, doesn't it?
Very nice.
Last line, there it is, mealy, sorry. Okay, so here's the key. So we're going to have S sub n. We're going to have x all over SV. Now I do want to say something with this. Could I have written VS?
Sure.
You could have. That's your design decision. Most people, and I don't know, that's the order they gave it to us in this little graph here. That is an arbitrary design decision on your part. But once you've labeled it, you stick with it. Right? So I'm going to do SV. How many of these V's will be non-zero? Only the last one, right? So the first three, I know right now, before I ever start, they're going to be 0. How do I start? It's the first thing I do. Reset, right? All right, so we're going to have S0. It's going to be the reset state. But I'm going to try to name it right off the bat. I mean, reset, I couldn't kind of just leave it there. Nothing's happened yet, but let's just get in the habit of saying these two things. This is what all of our states are really keeping track of. Which bit am I on? First bit, right? Which is actually, I'll call it the first bit. In our case, that bit is the LSB, correct? It's the least significant bit because it's coming in first. Is there a carry or no carry in the reset state? No carry yet, right? Nothing's happened. So this is really saying this. Now some of you are kind of like scratching your head, why is he working so hard on these names? Because if you know the name, you understand how the machine works and you probably get it right. Okay? Naming is really important to getting this. All right, so here we are, and I would encourage you on these, and I'll do it again down here. Show the math problem. So here's x. I don't know what it is, but I'm going to add to that the constant 2 producing the sum s. Right? And I'm just going to kind of work through this problem. And like again, on a test, could I just make this, instead of making it +2, move it over here, make it +4, +8, +6, some other constant? It'd be really easy for me to change this. And the state graph would change. A lot of things would stay the same, but it would change. Okay, so here we go. Let's put ourselves in the reset state. Nothing's happened yet. And we get a 0. What are we adding to the LSB? Nothing, right? We're adding 0 to it. So we should output a 0 and go to a state that has no carry. You agree? No carry here, output a 0. Right. Now, will I ever hover? No hovering, right? So we've got to at least always make at least one new state. So this is going to be state 1. It's going to be second bit, no carry, right? And we said if we get a 0, we would output a 0. And of course, the V bits are always 0 for the first 3 times. All right. What if I get a 1? So put yourself back in state 0. This isn't going to work. It's going to be all wet. Let's try it. What should I output? Right? If x comes in as a 1, I'm adding nothing to it. Can I output a 1 right now? Yeah, is there gonna be a carry? It's not possible to get a carry. You see that? It's gonna be a 0. What do you think?
Goes to state 1.
Goes to state 1? Can we reuse state 1? How many people think we can go here? We can. Because it's a mealy machine, we can just go ahead and output that sum right now. But notice that the state wouldn't change. I would still be second bit no carry, right? So it could go here. David?
So if we were to use a more, would it be different?
Yes. Yep. Yeah. Because the more we'd have to differentiate it based on the output would change. So the more machine would get bigger on this one. And again, remember that the more machines always kind of output late. They output coincident, or a mealy machine can output coincident with the input at the same time as the input. But a more machine, we have to clock it in and then we output it afterwards. So the timing would be different. There we go. So good. All right. So now we're done. We're done processing the first bit, right? You can forget about it. So our math problem, we've done 1/4 of our math problem, so to speak. We've handled one of the 4 bits. So now we put ourselves in state 1, and we get a 0. What should we output? We should output a 1. Will we have a carry? No carry, right? So we need to go to a state that remembers this. Get a 0, we're going to output a 1, and we're going to go to a new state, state 2, which is going to be 3rd bit, and there's still no carry here. So if I get a 0, I'm going to output a 1, because we're adding 1 to it. That's our constant. That's our number 2, really. So it shows up there. Like that? Okay, what if, on the other hand, put yourself back in state 1, which is there's no carry, and I get a 1 here. 1 plus 1 is 2, right? Actually, it's 0 plus 1 plus 1, I should really say, right? Keep keeping in count this. So it would be an output of 0, but I'm going to go to a state with a carry. Do I have such a state already? No. You see, I need to create a new state now. A new state's going to occur, and it's going to split right here. And if I get a 1, notice I'm going to output a 0. It's kind of weird. Wait a minute. Hey, I got something, and I'm outputting. Well, that number's really going to be stored in the state information. So in state 3, I'm going to be on 3rd bit, and now there is a carry. So we produced this carry. The machine's going to get a little bit more complicated. Not terrible here, but. Okay, have we finished state 1? Yes, we've accounted for 0, we've accounted for 1. So we're done with that. I'm halfway through my math problem. Right, I've accounted for the first 2 bits. Now it's going to get a little bit more complicated because there's 2 possibilities coming into the 3rd bit. So put yourself in this situation. If I'm in state 2, what's the carry condition here? It's a 0, isn't it? It's a 0. All right, what if it comes in as a 0? I should output a 0 and no carry, right? Do I have that state yet? No, I need to create it. S4, 4th bit, no carry. And if I get a 0, I output a 0. What if I was in state 2? Put yourself back in state 2. So I'm processing the 3rd bit. There's no carry so far. It comes in as a 1. What should we output here? 1, is there going to be a carry? No. Does that state exist? Yes, no? Yes. Yes, right? I can go to right here. So I'm gonna output, a 1 comes in, a 1 goes out. And I can still go back to there because it didn't change my carry. All right, we're getting closer, but now we have to put ourselves in state 3. So what's the condition of my math problem in state 3? Processing my 3rd bit, is there a carry here? Yeah, so there's a carry up here somewhere. Sorry, the board is really acting weird. It's wet, bad idea. Okay, so try to turn the color. What if the bit comes in as a 0? We would output a 1 and go to a state with no carry, correct? What do you think, Paul? Can we go to state 4? Yeah, right? Because state 4 is 4th bit no carry. So we can head over here. If we get a 0, we're going to output a 1 and head back to here. Do you see how this 1 is kind of now popping out down here? In essence, that's really kind of what's happening because the carry has stored that for us. All right, almost done. The last condition would be if I'm in state 3 and I get a 1. So I'm in state 3 with a 1, but there is, just erasing this up. This is going to be an output of 0 and a carry out. Does that state exist? Nope, got to make that one. So that's going to be here, S5, 4th bit, but there is a carry. So that carry keeps carrying on, if you will. Notice I don't output anything, or I'm outputting a 0, but the state is remembering that a carry is present. All right, now we hit kind of an important juncture. Which bit are we processing? The 4th bit. What happens on the 4th bit? We reset. We must reset. We're not going to make an infinite state machine. So if some of you, on your test, I'll just warn you right now, if you're like, I don't know what's going on, you keep making more and more and more states, don't. You're going to get fewer points if you do that. Okay? When we hit the 4th bit, we're stopping. We must go back to the beginning and reset. So all of these guys coming out of the 4th bits must return to reset. This is very similar to the other one that I almost did, or we started on the BCD checker. The same kind of reason. They must go back. You guys over here can't see that. So show you. Okay. Put yourself in state 4. So state 4. So I'm done. I'm done processing this. Great. If I'm in state 4, this is a 0, correct? There's no carry. And you see, can I kind of solve it like this? What is 0 plus x plus 0? It'll just be x, wouldn't it? So whatever comes in goes out. If a 0 comes in, a 0 is going to go out. And we're not going to overflow. We can't. If a 1 comes in, a 1 is going to go out, and we will not overflow. So whatever we get, we get back. Let's put ourselves in state 5 to finish this. So what's the condition of our math problem in state 5? We do have a carry. This isn't 0, right? This is a 1 up here. And now if I get a 0, I should output a, if I get a 0, I should output a 1, but there'll be no carry out, right? That'll be the end of the line. 1 down here. But what if it came in as a 1? 1 plus 1 is 2. We should output a 0, right? This is going to be a 1. We're going to output a 0 here. Something very exciting happens. What happens on V? For the first time and only time on this entire graph, V is non-zero. There's only one spot. That red V is the only V, right? Aren't all the rest of these zeros, zeros everywhere, zeros? Only right there. It's the only overflow condition. And there's not very many times. When will that be true? When it's a 14 or a 15? Okay, so now, should we try this? Can we run through this graph and see if we get the right answer? This is always kind of nice. What if you do this problem and you do it on the test and you think, hey, I wonder if I got it right or not? Generally on my test, you have enough time. You could do this. Okay, Christopher, pick a number between 0 and, say, 12. 11. Okay, so let's try the number 11. And the number 11 is this, correct? So the LSB would be a 1. Now, what is 11 plus 2? 13, right? So 13 would be that. This is what we hope we get out. Let's try it. Let's see if it works. All right, so we start here at the beginning, and I get a 1. Actually, let me do this kind of with the green pen. I'm just going to follow the flow of this problem through here with this. You see I would follow this path. I would get a 1. What would I output? So I'm going to output a 1, right? Great. Now I get a 1. What would I output? You see it would be this path right here. And I would output a 0. Okay. Now I get a 0. Ooh. You see I would follow this path right there. And I would output a 1. And then I get a 1. That would be this path, wouldn't it? And I'm going to output a 1. Hey, did we get the right answer? You see the number 13 arrived here. So just by going through this graph. So you can always check yourself and see if you get the right answer on these. And, you know, try a couple, make sure. Obviously, if you don't try them all, you don't know for sure you got it right. But probably if you try 2 or 3 at different sizes, you'll be pretty convinced that you got it right. That's pretty neat. I want to say that this is really very efficient. And you could do this really fast. If your data was coming in bit serial, I can't hardly think of a way to get this kind of performance. Say you had to perform this calculation on a number. You had to do y equals mx plus b. Just adding this b could be almost, as fast as the bits are coming through, I'm just doing it. It's almost like transparent. It doesn't add any extra time. It would just be a slight delay. And if you had a bunch of numbers coming in through, you could just be pumping these out really fast. All right. Think you got it? Hope so. What's problem 38 do? Well, it says, what if we subtract it instead of add it? Oh, yeah, I guess we could do that. Now this is a little bit weird. What would change if the math problem changed from addition problem to subtraction problem? Would we still have to keep track of which bit we're on? Absolutely, this would not change. But instead of having a carry or no carry, what's going to happen here? Yeah, it's going to be a borrow or no borrow. And you're going to loan. You're going to presume upon the future. But I just want to show you this in math. What if I was going to subtract 2? So say I had the incoming number was, say, 10. No, actually, that's a bad number, because it wouldn't be very interesting. I want one where I have to have some say the incoming number was the number 8, and I wanted to subtract the number 2, and I get this one bit at a time. So let's think about the math problem. What would happen here? 0 minus 0 would be 0. So we'd output a 0, and there'd be no carry or no borrow, right? There's no borrow going on. But I get to here, 0 minus 1. Well, shoot, now I don't know what's coming yet. You understand that? I don't know what's coming yet, but could I presume upon the future? Hope that somebody's going to eventually pay my bill? I always kick the can down the road, right? So what I'll do is I will assume that I borrowed against the next digit. What would he give me if I did this successfully? He would give me a 2, right? And what's 2 minus 1? 1. But you see, this guy's been borrowed against. So he's not just 0. What's he right now? He's really -1. Okay, he's kind of in trouble. So can I take 0 minus 0 when I'm really -1? No, do you see that he's going to have to borrow against the future? So he's going to go to a state of borrowing. Now, this gets a little tricky. When he comes, he's going to give him a 2, right?
That's really just a 1.
But I've been diminished by 1 by the guy before me. You see that he's actually going to be a 1 here. And so 1 minus 0, I should output a 1 there. So you can't figure it out. It's kind of postponing or, you know, thinking about what might happen in the future, right? And if I get to here, what's going to happen here? If I'm a 1 and I've been borrowed against, what am I really? I'm really a 0. And 0 minus 0 would be 0. And ta-da, that's the right answer, isn't it? See how I took 8 minus 2 and I got 6. But I was really just thinking about it one bit at a time, presuming upon the future. So it's really the same, a very similar problem. The structure will be very similar. But instead of having carries here, you're going to have borrows here. Did I make a problem? Hey, why don't you subtract 3? See how easy that would be for me to make a different problem on the test? And so I strongly recommend you get these two down pat. Chances are at least 50% that one of these will be on the test. Okay. Daniel?
What would happen when you're at like 0? Would you go negative?
Yeah, good point. What if I did this? 0, 0, 0, 0 minus 0, 0, 1, 0. What's going to happen when we're done with this guy? There's going to be a borrow out here. We are in debt. Minus 2 is going to be the number. And actually, it's going to look like that, which is the number negative 2. We're going to learn about that later. But, so you would end, just like this one ended, with an overflow condition. How's that guy going to end? In a borrow condition. Basically saying I'm negative, I'm in the hole, I'm in debt. So that's how it'd have to end. Now, what I would say is, you would have to, let's think about this. What if he delivered and the number was not 0, but the number was 16? What would happen in this last bit position? Do you see that? That would end up being a 0. Now, in terms of you guys thinking about, what is 16 minus 2? 14. You've got to give me the right, wrong answer, so to speak, right? Or the right in-debt answer. And so if it did have a 1, it would have been that. He never arrived. My Savior never came. I'm in debt. But anyway, that would be it. Okay? So it does have to function as good as it possibly can, assuming that somebody, that we're not going to go negative. And if we did, we're going to tell the world we did by saying, I got to borrow out of my last bit. So good question for Rest. Put you in. All right, fun. I've got a little bit of lecture to give you, and the last problem, which is the best. So here we go. This is a little section, section 5 of the textbook, 14.5, where we talk about what's called alphanumeric techniques. As our graphs get a little bit more complex, sometimes it's easier, especially when we have multiple inputs. Most of the problems we've had one input. I think a couple have had like x1, x2, right? But the most we've had for the different number of inputs was 2. I want to tell you that some real machines, and a real machine we're going to build pretty soon, it's going to have like this many. Now that would be really scary. Say you had just 5. Say you had 5 inputs to a machine. And you might have like your shaft encoder input, you might have a temperature input, you might have a pressure input or something else going on, a bunch of different inputs. Well, if you had 5 inputs, how many arcs would exit every state? 32. Now, 32 arcs exiting every state, that would be ugly. I'll just tell you, that would be ugly and messy and probably would fail to communicate. The purpose of these things is to communicate clearly the behavior of the machine. So as we get more complicated, it might make more sense, because this is another thing. You probably learned this. You cannot serve 2 masters. Okay? You will love the one and hate the other, or obey the one and disobey the other. Any given machine cannot respond to all kinds of things simultaneously. Something has to rule the day. What is the most important thing that I'm going to make the decision on? And that's how most machines really operate. And as a result, we can use, we're just going to use the letter to indicate it. And I'll show you some examples pretty soon. Another thing that happens regularly in real world machines is that they hover a lot. A lot of real machines hover a lot. Now, not these kind, but machines that control machines, Okay, let's think about this for a second. If I have a machine that's controlling a machine, like your engine, intake, compression, combustion, exhaust. Now, how fast can my machine, my electronic machine go? Super fast, right? Super fast. I mean, like millions of times a second, and even billions of times a second, right? So even though that engine's cranking at what, 6,000 RPM, you're redlining this baby. Hey, my FPG, my electronics, my fit programmable gate array or whatever, it can keep up with that, like not even breaking a sweat. And in fact, it's going to sit there and twiddle its thumbs most of the time until that crank arm gets over to this position where I need to fire the spark plug or something, right? So I actually wait a lot in real world machines. I'll just say that. So let's not show those. We'll only show exit conditions to save space and communicate clearly. If you don't see an exit condition, we're just going to stay right here. Okay? And finally, an arc with no label at all is what we could describe as unconditional. We're going to need some of these in just a minute. And it will happen on the next clock event. So it's like, I will spend one clock cycle in this state, and now I'm out of here. Maybe I just have to reset something, or I just have to pause for just an instant, and then I'll go on. So here's kind of a cool one. This is like showing this. This is like forward, reverse, 3 different states here. This is the partial, okay? It's like if I'm going forward, you see I'm going forward. If I'm going in reverse, so I'm counting up, 0, 1, 2. I'm going in reverse, I'm going 2, 1, 0. Now, because there's 2 inputs here, I cannot serve 2 masters. So I have to decide, one is going to have to rule the day over the other. And that's what this second graph is kind of saying. Notice here, and I could have left it here, it's like, hey, I will stay in state 0 unless I get a forward command, which pushes me to here, or I get a reverse command. Now this explicitly says that. I wouldn't necessarily have to say that, right? If I don't get a forward, don't get a reverse, I stay there. But now, do you see how these 2 arcs, who's going to rule the day? What if I say forward and reverse at the same time? Not a good thing to do your transmission, right? Going forward and then shove it in reverse. Okay. Yes, I don't have a transmission anymore, right? But you see, forward rules the day. And only if forward is not true will reverse go. So that was a way of describing its priority. If you have multiples, you've got to decide which one is going to have the priority, who's going to rule the day. Okay? Here's another really fun one I got from another textbook. Now, this was like a 1950-something Thunderbird. It's like cool Thunderbirds. They had the coolest thing ever. Their lights, when you turned on the turn signal, went boom, boom, boom.
So Thunderbirds.
Yeah, isn't that just so cool? Back in that day, it was really, really cool. And this is the state graph that shows that. Now, what controls the turn lights on your car? Well, it's the turn signal, right? Am I a left turn signal? That would be left. And not right. And what's this one? Well, that's your hazards, right? Where it's blinking both of them. Boom, 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 boom. Oh boy, that was fun. So this is, these are it. These are the different states. But I would guess if I let you stare at that for 10 minutes, you could probably understand it. Do you see how the words help you understand it? By having the word left on there for the left turn signal, right on there for the right turn signal, and hazard on there for the hazard signal. And what do you suppose, what does this mean? Not. The hazards are not on, right? The right is not on, but the left is on. So again, when we have multiple signals like that, we have to give a priority. Who rules the day? Well, who should rule the day? The hazards should rule the day, right? If the hazard's on, that's going to dictate everything. That's the most important. So you can see that hazards kind of take over. But those are this would be the 3 different lights on the right side. Right 1, right 2, right 3, right 1, right 2, right 3. So I just want to say that as machines get more complicated, we like this alphanumeric thing. It communicates a little more clearly. And otherwise, how many arcs would we expect to exit from every state here? Well, it's kind of interesting. There's 3 signals, right? Left, right, and hazard. If we did all possible combinations, how many would that be? 8. Yuck! You know, and that's not really what dictates how this thing's gonna go. We're just gonna list the ones and whoever rules the day enough to know precisely what's gonna happen. Okay? So that's good. All right, now for the last one. This is fun. Joshua, would you read this for us?
A sequential circuit is to be used to control the operation of a vending machine which dispenses a 25-cent product. The circuit has 3 inputs, N, D, and Q, and 2 outputs, R and C. The coin detector machine and the vending machine are synchronized with the same clock as the sequential circuit you are to design. The coin detector outputs a single 1 to the N, D, or Q input for every nickel, dime, or quarter, respectively, that the customer inserts. Only one input will be a 1 at a time. When the customer has inserted at least 25 cents in any combination of nickels, dimes, and quarters, the vending machine must give change and dispense the product. The coin return machine gives change by returning nickels to the customer. For every 1 output on C, the coin return machine will return 1 nickel to the customer. The product is dispensed when the circuit outputs a single 1 on output R. The circuit should reset after dispensing the product. The customer inserts a nickel, dime, and a quarter. The circuit inputs and outputs could look like this.
Okay. Now, it's kind of cool here. If you think about it, we got a vending machine. So we got a coin here representing some amount of money, and maybe we slide it into a slot, and it gets sorted, right? And I guess dimes would be the smallest, right? They'd fall through the smallest opening. We would make that nice and skinny for us. And then what? Nickels would be next. Something like this. We'd see 5 cents, and the big old quarters would come down here. Now, I'm going to be kind of simplistic with this. We could maybe have a photo eye that sees when a coin drops through there. You have to probably be a little more sophisticated so you don't get washers or something else, but we'll just keep it simple for now. Now, I want you to notice something. Are there lots of nothing happening states here? Why would it maybe be like that? Yeah, is our electronic circuit probably going to clock it really fast compared to people putting coins in? Yeah, we're just buzzing. So we're actually going to see, it's a fairly rare event, if you will. You see what's happening? Nobody entered anything. Oh, somebody put in a nickel here. Okay, so we count that. We're going to have to keep a track of that. Now, what is this machine going to need to keep track of? I think it's pretty obvious. How much money, right? Now, what's the smallest denomination we accept? 5 cents. So could we have a 5-cent state? 10 cents, 15, 20, 25? Yes. Okay, so we're going to start here. What kind of machine, by the way, is this? Mealy or more? I think they said more, right? Right here, design more. All right, so we need our key. And key's going to be S to the N. The output's in here, so C and R are down here. And now, this is going to be a little bit weird. But we're going to label our key like that, NDQ. We're going to use this alphanumeric style. A means it was a nickel. A D means it was a dime. A Q means it was a quarter. Now, thinking about it, you'd say, wait a minute. I should have, from every state, if I had 3 inputs, how many arcs should exit? It'd be 8 of them, right? You see that that's totally impossible under this physical, realizable world. How many are ever possible to come at once? Just 1. So that's good to know. All right, so really the S0 is the 0-cent state, and I certainly don't want to just give them any money or give them the product, right? On the coin return and returning the product. But if I get a nickel, I should go to the 5-cent state, which I'm going to call state 1. And I certainly don't want to give them anything yet, but I'm counting their money, right? I'm going to keep track of it. Now, if I had a nickel coming out of here, I would go to state 2, which is really the 10-cent state. Then I don't want to give them anything, but how else could I get to this state from S0? A dime, right? You see how a dime would take me here. So I am running out of time. We'll go this pretty quick. Everybody see what I need here? I'm going to need every 5 cents. So I'm going to need a 15-cent state. I'm going to need a 20-cent state. I'm going to need a 25-cent state. Now that's kind of a special state here. So S3, S4, S5. All of these I'm just kind of keeping track of money. And you see that I could end up here on a Q. Coming out of state 0. Nice. All right, nickels moving on 1. I haven't shown you everything here. You're going to have to fill in, you know. Dimes skip over a state, don't they? So like if I was here and I got a dime, where would I go? I'd go to 15, for instance. Just showing you a couple of them. What's kind of the worst case scenario? Now we're going to be nice. We're not going to steal the kid's money if he does something stupid like this. Like, kid, come on, put the quarter in first. You're done, right? Why did you give me 15 cents just so I can give it back to you? And that's really what's happening here. So notice what happens when we get this quarter. How many cents do we have? We have 40 cents, right? So we've got to get it down to 35, 30, 25 by giving him 3 nickels. That's how we're always going to give change, a nickel at a time. And once we've dropped to 25 cents, then what do? Give them their candy, whatever it is, the product here. All right, so can anybody see, that was 40 cents. Do I have a 40 center up here yet? No, what's the worst case? Does anybody see what the worst case would be?
2 dimes.
How about if I was sitting here with, like 2 dimes, and then they give me a quarter? Like, come on. But if they did, you see that what state would this have to be over here? 45 cents, right? So I need a 45 cent state. But that means that I would have to have a 40 cent and a 35 and a 30 center too, right? Do you see that? Yes.
Could this in essence be an infinite state machine if we just keep putting more money in?
Again, I want to say that all these machines can continually do their job, time after time after time. As far as, you know, this being an infinite state machine, is you can keep reusing it until it breaks, right? But I want to say that there's not an infinite number of different states. We always make a finite number of states. I'm not going to show you a machine that keeps having more and more circles all over. This is the most circles we're going to get. So I want to say that 45 cent is it. That is worst case scenario. We can respond to them faster than they can respond to us. Kind of the idea, although this brings up kind of a fun point here. You know, if they start shoving in quarters as fast as we can, right? Again, wait a minute. We're not even going to break a sweat, right? We can do this a billion times a second, so I mean, have fun. Shove them in there as fast as you want. I don't care. From the electronic standpoint. Now, I want to say, actually, you guys are mostly mechanical engineers. This may not be, well, we'll talk about an issue here in just a second. What happens out of the 45 cent state? What should we do here?
Give them a nickel.
We need to give them a nickel, right? That's what we do. We have a stack of nickels that we're gonna give to them. So we give a nickel by putting a 1 on C. So we're going to put a 1 on C and a 0. We're not going to give them the product yet, right? We're going to obey this. Now, in so doing, I should drop to the 40 cent state, right? Now, what do I put on this arc?
Not nickel.
Nickel, dime, quarter?
Not
Now, wait a minute. That's them putting it in. Do I wait for them to put in a nickel to give them back a nickel?
Not nickel.
Not nickel? That's not a bad idea. All right, this is kind of a trick question. Yes! Way to go. Connor got it right. It's unconditional. Don't put any label on here. We're going to obey. Our machine is going to do what it promised to do. And that is give you a nickel. I mean, unless it jams or something, and then you should report it and we'll give you your money back. But if it's working properly, right, I just gave you a nickel. And I've dropped to 40 cents. What should we do in the 40 cent state? Same thing, right? Unconditionally go to here. And here I should unconditionally go to here, and here I should unconditionally go to here. Okay? So now there's a bunch of arcs heading over here. Does everybody get that? And nickel, dimes, and quarters from some of these states. But these guys just take care of themselves. Now, what happens in the 25-cent state? We should dispense the product, right? Right here. And then do what?
Okay.
Unconditionally return home. And let them put in some more money. All right, now there's two practical things that we have to talk about, which is kind of fun. How fast are we clocking this machine? You see, they kind of represent, each one of these represents a clock. Now I want to tell you that, again, that's no problem. I can clock it 2 billion times a second. Most circuitry today, I could do that. Can I shoot nickels 2 billion times a second?
If you're trying to kill
Maybe not. Okay, this would be worse than a machine gun if we could do that. Right? So there's a practical nature to this. Our electronics is so fast, but our mechanics maybe not so much. I mean, we have to deal with inertia and forces and recoil and,
just build a railgun to shoot.
There we go, a railgun, that would be pretty cool. So we probably would have to limit how fast we ran this thing, right? Maybe at the, I don't even know. How many nickels a second could we? Probably it's some fairly slow mechanism. I want to say the practical nature to this is in the event it's not shown in this graph. What I would like to do to make this a more practical machine is add one more output. I'll call it the hatch. Okay? And I open the hatch right here. Okay, can you imagine a little hinge here? It's going to open the hatch, so if any coins come in, I'm just going to feed them right back to you. I'm not going to process them so that I don't steal your money and we don't get confused what's going on. And if I added this one more output here, he would turn on in each of those states. Does that make sense? If I'm in any of those states, I'll open the hatch, we'll just dump any remaining coins down, and now I can slowly kick out nickels to you at some sensible pace, right? And then when I return back to there, then I'll start over again. We'll lower the hatch and allow you to put money back in and not just go down the coin return. So I like to think about some of those practical things. Now I will tell you on this particular problem, they ask for a table. And this table is a little bit weird because we use the alphanumeric notation. So I'm going to try to help you with that. This is up on Moodle. You can download the PowerPoint. You see it. I would recommend you do. And notice if we're in the zero state, or this is the amount of money. This is the naming in my states. I think it's the same as what I've done here. But if we don't do anything, if nothing comes in, what do? We just stay there, right? But if I get a nickel, I go to S1. If I get a dime, I go to S2, and if I get a quarter, I go to S5. You see that? And what do I output in state 0? 0, 0. So it's a little bit different format. It is kind of more of a short, fat table, but it'll be handy for us. The answer's not in the back of the book, but fill that in and you'll get the problem. So, yay, I got through this. Will you guys do me a favor? If you guys know anybody in the 830 section, you share with them what I just shared with you, and they have an answer that you guys don't know, and so they can share with you. Because I ran out of time. I did the BCD one completely with them, but I skipped this problem. So help each other out. We'll see you on Tuesday.